let's have a little fun with some basic electronics for a change. And this is actually going to lead somewhere. In electronics, in the first phases, basics, they teach us to transmit radio waves. And without getting real complicated, basically, to transmit a radio, you have to have some means electronically of producing some kind of signal. And then you attach that device to an antenna. And, well, let me draw an antenna here. I can't draw a straight line, so I'm going to use this. And this way I can make it a straight line. And there we go. Look, a straight line. Wow, I'm impressed with me. So you'll come in. I have to do another line here if I can. There we go. We come in, and to that antenna we've got drawn over there with a single line. Oops. There we go. Boy, this isn't going real well. Be kind, it's my first time. We just attach. Down here would be our source of our radio, where we create the voltage, etc., that's going to attach to this antenna up in here. So down in here, don't worry about what that is. Let's just say it's magic. So the voltage comes out and connects to the antenna, and then this antenna radiates energy off of it. I'm not going to. This would take me forever to make a bunch of little lines up here representing energy coming off of them. And I'm not a great drawer. Can't draw very well at all. That's why I'm doing this. But here's the energy coming off the antenna. Make out like there's 4 of them through here. And then that goes and touches the receiving antenna and induces a voltage into it that then is picked up on the receiving side in the antenna and fed to the box where the magic occurs. We won't discuss that magic. I'm not going to get that technical on you. And what they teach us is for any frequency we want to transmit on, we make this antenna equal to that frequency. In basic radio, that's what they tell us. We'll get rid of that one. We'll get rid of the box. Let's get rid of our line too. So here's our antenna. And we have a calculation where we decide what frequency we want to transmit on, and then it'll tell us what length antenna we need. And all you have to do is go get a hunk of metal and cut it from end to end equal to that length, and then zap it with our radio frequency, usually in the center, usually, but not always, usually in the center. In truth, you're going to cut this wire in half right here and attach ground on one side and your signal on the other, in truth. But let's not go that deep. Let's just say this is a basic crystal radio. A rock is vibrating and creating a frequency, and we want this antenna to be resonant. That's what we're looking for, resonant, equal to. If you have a tuning fork that's a certain pitch, let's say middle C as a musical note. If we put another tuning fork a foot away on in a vacuum, so that there's no conduction of vibration between the two of them, and vibrate one tuning fork, the other tuning fork will start vibrating too. It's called sympathetic vibration. Because they are physically tuned to the same frequency, they really, really enjoy taking up that frequency any chance they get. So a nearby object resonating at that frequency will cause the second identical object to also resonate at that frequency. That might not be a good illustration, but I'm trying. So basically that's what's happening here is we cut this antenna for the length we want to transmit on. We cut the antenna on the receiver to that same length. We zap the transmitting antenna with radio frequency energy. It casts off that radiation. It hits the other antenna on the receiver, which is just perfectly tuned by its length to resonate at that frequency. And so it picks up the RF energy and then transmits it into the receiver, where we amplify it a couple of times, take the intelligence off of it, and use the intelligence. To figure out those things, this is a wavelength calculation here, frequency and wavelength calculation. And that's what this does, is this tells us what the physical length in centimeters, inches, feet, millimeters, meters, kilometers, the antenna has to be for the frequency to be perfectly tuned. And when we say tuned, that means it is exactly equal to the wavelength for that frequency. If it's untuned, it will be something other than that, and it will never work as well as if it's tuned. So at 433 megahertz, we're going to use some of the frequencies we use in drones here. Let's just pick 3 of them for kicks and grins. I've actually already picked them, and again, you'll see why at the end of this. So at 433 megahertz, our antenna needs to be 69.236 centimeters from end to end. 69.23 from right here to right here. And it will be resonant at the frequency of 433 megahertz. If that piece of metal comes into contact with radio frequency energy of the 433 megahertz flavor, it will soak it up like a sponge. And I'm going to write some of these calculations down real quick. And let's cut off the decimal. Let's not be precise. Let's be accurate. So 69 centimeters. For 433 megahertz, the frequency length is 69 centimeters. Oops, centimeters. Go back to our calculator and look at 915 megahertz. That's 32.764 centimeters. Let's use the whole number here. Let's not do decimals. 32 centimeters. So for 915 megahertz, the frequency length is, what was that, 32 centimeters. Wow, the old brain's working a little better. I think I'm getting over the concussion after 6 months. Not over it, but better. And then just for kicks and grins, let's look at 1280 megahertz, 23.421, but also that could be 1.2 gigahertz. It's the same frequency, actually 2 1.280. Look, the wavelength is 23.421 centimeters. We're just converting megahertz into gigahertz there by moving the decimal place 3 positions to the left. If we want to convert gigahertz into megahertz, we move the decimal point 3 positions to the right. It's that simple. It's working in base 10. But anyway, we won't get into Boolean algebra or anything like that here. So 23.421 centimeters. So 1280 megahertz, or we'll just write it here, 1.280 gigahertz is equal to, what's that, 23 centimeters. Yikes, how about that? 2 weeks ago, I'd have to keep looking back and forth at this to remember it. So we took away the decimal point. So basically what we're looking at now here is, if we want to transmit and receive at 433 megahertz, we have a 69 centimeter piece of metal that we're going to use for an antenna. 915 megahertz, the antenna is going to be 32 centimeters. 1280 or 1.2 gigahertz. Whoops. Actually, that is true right there. It is 1.280 gigahertz. If it were 1.2 gigahertz, this would be 1200 megahertz, not 1280. So we're trying to match these. And this again is frequencies we use on our drones for control link, video. It's a video transmitter and an RC control transmitter. They're just transmitters. And so for 1.2 gigahertz, 23 centimeters. So you can see a lower frequency has a longer piece of wire for the antenna. As the frequency goes up, the antenna becomes shorter and shorter and shorter in physical wavelength. Therefore, our piece of wire we're going to cut for transmitting and receiving antenna becomes shorter and shorter as the frequency goes up. That's one of the reasons, we'll go back over here, this is kind of a side issue, but that's one of the reasons when we talk about, let's look at a vertically polarized 433 signal, and let's see what we can play with over here that might work for my purposes. And this is going to be extremely out of scale. Let's drop this in here and call it, oops. Well, I guess that's an error. I was going to drop that in and call it a house. There we go. We'll call it that, a house or a hedge or whatever. And this is our 433 megahertz signal. And if you notice in our calculations, our 915 is just about half of our 433, but the 1280 is not half of the 900 because they're much more close in frequency. So a half, and then this 23 is about a third of our 433. So our our 915 megahertz signal oops, I think I'm being a little anal with this, trying to get it perfect for you, is approximately, oops, half the size of the 433. Okay, it's slanted a little, shoot me. And it's not exactly at the bottom either. Such be life. And our 1.2 gigahertz signal is about a third of the, let's see if I can put this on the other side and even get it close to the bottom correctly. There we go. Yeah, they're not lined up. That's the way I draw anyway. So you can see here while we talk about penetration a little bit on the video transmitters. With a very large wave, this house will not block this tall wave. I guess I could have made this just a little smaller so that it could be shown that it, right now it shows it's blocking both the 915 and the 1.2. You can't see it from over here because it's shorter than the house, so to speak. And that's what we talk about in penetration. I should have drawn this so that this house was just right in here for size, and it didn't block the 433 or the 915, but it did block the 1.2. That's just a little bit of a side issue. What I want to get back to is this frequency calculation. Now then, I don't know if you've ever heard people talk about quarter wavelength antennas, half wave antennas, full wave antennas being shown here. Let's go back to our 433 for kicks and grins, our 69 centimeter piece of wire. So you can see for a 3/4 wavelength antenna, we find 3/4 of that number. Let's go for half wave. 34 versus 69. It's almost exactly half. I bet you if I took out a calculator, it would be exactly half. And that's why they call it a half wave antenna. And then we have quarter wave antennas, which will be, the physical antenna will be 25% of the length. And a eighth wave antenna would be the frequency divided by 8, and that's how long it would be. All of those particular antennas, except for one, will pick up this frequency really well. A 1/8 wave, we don't really go lower than that because in truth, without getting deep into it, mostly we use half wave and quarter wave antennas, and we do that because of size constraints. But a quarter wave antenna, although it is resonant to the frequency of 433 megahertz at 17 centimeters, and will pick up that signal well, it really will not pick up the signal as well as a half wave. And let's not get deep into these, because these, especially the 5/8, are some special antennas that we don't use in drones. We use straight dipoles. We also do use circular polarized. That's a whole different thing. The frequency wavelength still is the same. Wavelength never changed for the frequency you're wanting to transmit on. A half wavelength antenna will really pick up about twice as well as a quarter wavelength. But if we had, let's say, a half wavelength antenna needs to be 34 centimeters and a quarter wavelength, it needs to be 17 centimeters. Something there in the middle of those two, like a 20 centimeter piece of metal, will not pick up that frequency well at all. As you shorten the length from 34 centimeters all the way down through where you get halfway to your quarter wavelength, the gain of the antenna will decrease and become worse as you pass the halfway mark and move back towards the 17 centimeters for the quarter wavelength. It will pick up better and better until it gets to the quarter wavelength. Although at a quarter wavelength, it won't pick up as well as it does at a half wave. It's still more resonant than any of those lengths in between. I hope you follow me on that. It's really important how you cut your antennas. Then, of course, we have the full wavelength, and these are the frequencies we measured out there when we were doing our calculations, and we wrote down right here 69 centimeters approximately for 433, 32 centimeters for 915, and 23 centimeters for 1280. If we put down our, those are, let's, I guess we can label those. This is the frequency. And this is the wavelength. Let's modify that just a hair and say this is the full wavelength. And if we look back at our frequencies, I'm just going to do this real quick for half wave on 433. Full wave on 433, 69. Half wave on 433 is 34. So we'll come back out here and we'll do half wavelength. Whoops, didn't want a tab there, I want a tab here. And so my half wavelength was 34. Oops, wrong place. We can get rid of it. Well, we'll leave it. 34 centimeters for our 915. Half wavelength is 16 centimeters. And for our 1.2 gigahertz or 1280 megahertz, our half wavelength is 11 centimeters. Physically, cut a wire to those lengths. They will resonate at those frequencies and be very good antennas and receivers. Okay. There's really only one major problem with this. After you go through training for radio frequency and stuff, your basic training, and come to the next level in your training, what they tell you is, oh, you know, what we told you in that last class was a lie. In truth, if we look at full wave antennas, full wave dipole, a straight piece of wire. Antenna theory here, full wave dipole. If the length of the dipole, total wire, equals the full wavelength lambda, then it is called a full wave dipole. If a full wave dipole is used for either transmission or reception, let's see how the radiation would be. You see, here's your standing wave on the piece of wire. We have a full half wave of positive and a full half wave of negative. Same wire. Those two are going to cancel each other out, as it says right here. The full wave dipole with its voltage and current distribution is shown here. Both the positive and negative peaks of the wave induce positive and negative voltages respectively. However, as the induced voltage cancel each other out, there's no question of radiation. Ooh, what's he saying? A full wave dipole cut to the exact frequency length of the frequency that we want to transmit it receive at doesn't work. Wow. Gee, Chief, you told me in phase 1 of this training that that's the way we made a radio. Now, why did you lie to me? It was fun going through military electronics training. Let's see, down here they talk about the voltage pattern when it induces its positive charge and negative charges at the same time cancel out each other as shown in the figure. The induced charges make no further attempt of radiation since they are canceled. The output radiation will be 0 for a full wave dipole. Wow. So what do we get? As there is no radiation pattern, no directivity, no gain, the full wave dipole is seldom used as an antenna, which means though the antenna radiates, is just some heat dissipation, which is a waste of power. There's some translation problems here too. Wastage of power. So the only thing you're going to do with a full wave antenna on your transmitter is produce heat. Granted, in this case, it's probably going to be in the antenna more so than in the final output amplifier. Therefore, you're probably not going to burn it up. That's neither here nor there. It may still. Which means, though the antenna radiates, it is just some heat dissipation. The disadvantages of a full wave dipole antenna is heat dissipation, wastage of power, no radiation pattern, no directivity, no gain. Due to these drawbacks, a full wave dipole is seldom used. So if we look back at our calculations over here for a, right here for full wave, technically all of these physical length measurements we calculated here won't work. They'll just produce heat. So at 1280, a 23 centimeter antenna won't radiate. You have to go with the half wave. You have to go with something less than the full wave. A half wave antenna, we say, generally has a gain of 2.5 dB. And a quarter wave is like 1.5. And an eighth wave is probably 1.25. As you get away from, as the antennas get smaller, of course, there's less physical length there to induce the voltage in, although it is resonant to the voltage frequency. There's just not as much there, so you don't generate as much voltage in the receiving antenna. So the best one to use is a half wave antenna. Full wave doesn't work at all. Half wave. Cut that 1280 megahertz piece of wire to 11 centimeters, half wave, you really do get your best transmission and reception. And we do cut them down to quarter wave, but we really don't go any lower than that much because you just get less efficient. So most antennas are half wave or quarter wave. None of them can really be full wave as far as a dipole is concerned, a single piece of wire. So let's keep our calculations right here and let's go up and look at the point of my video. When I ordered my Dragon Link stuff, on the order page it asks you what length of basically the coax from the transmitter receiver end to the antenna end. I trust my soldering, so I can take a big piece of coax like this and use it over and over. But
when I ordered the Dragon Link, I was just interested in getting Dragon Link in my hands. And so I ordered what they had available. And it was actually this one right here, I think. Oops. And it's a little shorter than these other coaxes. Then I ordered 3 more receivers, and they came with these really long coaxes. And then after I started working with the Dragon Link, I wanted some shorter antennas. Sometimes the receiver itself will emit, whoops, wow, don't like doing that, will emit RF energy too, and you really need to get the receiver physically out on a wing as well as the antenna. So I ordered some little antennas like this. The shortest one they sell is a little, I mean, it's about this much. It's just the connector on top of a receiver. They're $15 a piece. And then the next one is 6 inches, and then this one is approximately a foot. So I ordered 3 of these, $45. Reason for that's the coax that's going between them. So I got 3 of these. Here's one of them. Okay. Come out wherever you are. Anyway, I've got one on the bench over there. Oh yeah, I already did the other one. It's on the receiver over there. I'll have to get it off. So this is one of the antennas that came from Dragon Link. Having been exposed to these antennas for several days before that one came in, you'll notice the first thing that struck me when I pulled these out of the box was, wow, wait a minute. I must have ordered a 433 megahertz antenna instead of a 915 megahertz antenna. Oh, crap. I'm either going to have to get these exchanged, or I'm going to have to just buy some more. Frequently when I make mistakes, I just take it on the chin and eat the extra charge and go on. Bless myself out and cuss myself for a few days, but go on. So I went, boy, I needed 915 megahertz antennas like the ones that came with the original, and I screwed up and ordered 433 megahertz antennas. Well, let's look at this real close. So I was looking at this antenna that's so much longer than my 915s that I had just gotten from Dragon Link, and I'll have to work at focusing this. And I looked right here on the antenna, and the first thing I saw and read was, this is a 433 megahertz Dragon Link antenna. I ordered the wrong thing. And then I went to their order page. They're not labeled as 915, 433, or 1.2. And if you look at this antenna just a little deeper, you'll notice it also says that it's a 900. I'm not going to pull on that to get that completely out of there, but whoops, little focus please. But you can see it says 433 megahertz, 900 megahertz, and 1.2 gigahertz. What? Yep, that's exactly what it says. So this antenna is designed to work at 433, 900, or 1.2 gigahertz. They don't sell a 915 megahertz antenna. They don't sell a 433 megahertz antenna, or a, well, I guess this one actually is, or a 1.2 gigahertz antenna. They sell one antenna that works for all. But here's the rub. I taped this antenna down to my cutting mat on the centimeter scale. And if you look, this antenna, if I've got it and this will focus, got it right there, and this antenna is it's just a little under 31 centimeters long. Okay.
So let's go back up here on the screen and look at it. That pretty much fits our 433 megahertz half wave antenna, 34 centimeters, just under. And I'll tell you the truth, in wave propagation, them being exactly to the nth degree on the centimeters isn't as important as they are a multiple of the wavelength, approximately a multiple of the wavelength. Probably this antenna really needs to be 1, 2, 3, 4, whoops, 1, 2, 3, 3.5 centimeters longer to work at its optimal. It's going to work fine at this, at just under 31, barely under 31. But look at this problem. If we take this antenna as it is and put it on our 915 megahertz system, it's a full wavelength. It won't radiate. It will only produce heat. How about that? To work well on a 915 megahertz or 900 megahertz, as this says, we can go over here and look at this real quick. Instead of 915, let's do 900 here. And you'll see for full wavelength, 33 centimeters. This is just under 31. It is practically that. It is not the half wavelength, even for 900 megahertz that's written on it. It's not 16 centimeters. It's twice that length. So picking it up out of the box and looking at it, I just immediately knew this thing isn't cut right for a 915 megahertz dragon link. At 915 megahertz, this thing is practically a full wavelength antenna for 915 megahertz. So then I started searching on the internet for cutting a dragon link antenna. Receiver antenna installation from Dragon Link. This doesn't even tell you that the antennas they sell are for 433, 900, and 1.2. And nowhere in here does it say a thing about their physical size. So, of course, I thought, well, somewhere else on the internet, they're going to be talking about this. FPV Pro, that's the same place. RC groups, how to build your own transmitter antenna, Dragon Link instruction manual. Come in here, the only thing it tells you is same thing that other document says about it should be vertically polarized. There is a up on these and a down, but it doesn't say a thing in here about sizing them. There's no place on the internet. This is that little one they do sell with just a short. It's got the connector right on the antenna. You can buy those 6 inches, 12 inches, and then above. that was just an aside. So nowhere on the internet, I said, well, how about sizing a Dragon Link antenna? We're right back to the receiver antenna separate installation, and everything here doesn't talk anywhere about the fact that, in my humble opinion, if you have a 915 megahertz system or a 1.2 you're going to use this antenna on, you're going to have to cut it, especially for the fact that it is currently shipped at 31 centimeters, which is basically a full wave to 915 megahertz, which doesn't work. Not too sure whether or not it creates heat in your receiver as much as in the antenna, but it could do both. If it creates heat in your receiver transmitter, it's the transmitter that you're talking about here. You don't create heat if you have the wrong antenna on the receiving side. It's your transmitter. If nothing else, it just makes the antenna hot. You don't get anything out of it. And I can't find anywhere on the internet in Dragon Link's documentation or anybody's videos, anywhere, anything, no matter what I do, that you should cut these antennas. Now, of course, just going to see if antenna design, primary, nah, this doesn't get down into it. Of course, I saw, as I stated, that these antennas are not the correct length immediately because I've been working with the 915. So when they came out of the box for me, I knew they weren't right at all. I knew that I needed to size them for best transmission and reception. I needed to size the 915 down to 16 centimeters. Approximately. Remember, we took the decimal point away. And if I was wanting to use these antennas on 1.2 gigahertz or 1200 megahertz, I would size them down to 11 centimeters. And basically you cut that in half on each side of the antenna, 8 centimeters on one side of the midpoint, 8 centimeters on the other side. So I looked at the construction of the antenna and said, boy, I hate I'm going to have to cut these. I'm glad that I was trained enough to look at them from the get-go and go, wait a minute, those are not the right antennas. Then I went up on their website. They don't sell individual frequency antennas. They sell these antennas for 3 different uses. Then they don't tell you you're going to have to size them. Let's see, 11 centimeters on 1280. 11 centimeters on 1280. Let's go 1280 megahertz here and look at quarter wave. What we're looking for is 11 centimeters here. That's not 11. A half wave would be. So to use these on a 1280, we would have to cut them even shorter than if you're using them on 915 megahertz. You'd put 5.5 centimeters on each side of the midpoint for 1280 operation. In my experience and training. And so let me show you real quick what I did to cut my antennas.
And what I did is I took one of my original 915 megahertz antennas that came directly from the factory, and I cut this little piece of this tie wrap right here, and then I pulled the antenna tube off of it, and I measured this length. I found it not to be exactly tuned right either. It is actually, just a second, it's actually just a little under 7 centimeters, and it should be 8. And I kind of screwed up because what I did was I took this piece, turned it around, and laid it down. I'll have to move my camera here. Laid it down on top of the new antenna right here so that the centers were together. And I just moved the antenna out and cut it right there. I shouldn't have done that because this antenna is not tuned correctly from the factory for 915. It needs to be just a little bit longer. So the one antenna I did cut already is the one over here on the Sky Hunter to 915. It's not cut perfectly. It's accurate but not precise. The next ones I've cut, I'm going to cut 8 centimeters on each side, and hopefully they'll be better tuned than even this one is. How about that? So in my humble opinion, if you take this brand new antenna out of the box, don't pay attention to what you're doing, don't really, like me, immediately know something is up here, that's too big, and you go ahead and put it on your 915 megahertz system, it's going to become a full wave antenna, and it's not going to work well at all. I'm not going to tell you that it's going to do damage. I don't know that for sure. But I do suspect it's not going to work well at all. That's, of course, why these other ones were cut down to 915 in the factory. They're not cut precisely. They're cut accurately, about the way the electronics industry does it. But this antenna on a 915 would be bad. And you put it on a 1.2, you're not going to get good transmission or reception either. Is that not crazy? Nowhere on the internet can I find any reference to this, any documentation from Dragon Link or anywhere else that you need to cut these antennas down when you receive them. You can see that they were done at the factory for their 915 system, but there isn't even a little note in the box that says this antenna is perfect for 433 megahertz but must be modified for other frequencies. There's nothing. There's nothing anywhere. I don't find a video on YouTube about cutting Dragon Link antennas, but obviously you can see this one was cut down from in the factory to 915. It obviously should be done. And again, I'm not going to tell you this antenna is going to hurt your transmitter, but I don't think the transmission out of it will be very good at all. So the only thing I'm trying to do here, I'm not bitching about this, because to me, exactly as I took it out of the box, as soon as I unfurled the 2 leads on each side, I said, that's not right for 915. That's too big. I knew it immediately, but I don't think a lot of people not trained in electronics are going to recognize it that quickly. I think some people will take that antenna as it is and put it on their transmitter and then have crappy operation and not know why. That's why I'm making this video. By all means, if you don't have some way to cut it to 8 centimeters on each side, and it's, to be precise, there's a decimal there too. It should be 8 point something something something. I'll find that exact calculation here in a second, But I don't see anybody else making a video or anything telling you to cut these antennas or how to do it. Now, how to do it, you take an X-Acto knife or a set of dikes and you go clip. As far as physically cutting them, it's not that complex. It's just the knowledge to know that you need to cut them is what I see lacking here. And again, I'm not complaining. I immediately knew I had to do something when they came in the box the way they came. But I'm making this video so that others not trained have a heads up. Check your length on your antenna for the frequency you're wanting to use. Try to go for a half wavelength physically. Make sure it's somewhere close to that. After I cut the antenna, of course these came from the factory a little short. They're not 8 centimeters, 8 point something centimeters on both sides. I can't lengthen them. My wire stretcher, I lost it years ago. So I can't stretch wires. But the new ones out of the box, I can cut more precisely than the factory cut on these antennas. Now let's look back up at the screen real quick.
And the way I'm going to cut mine in the future is 16.382 centimeters. And if you divide that in half, 16.382 centimeters divided by 2, I'm going to make the, you see, I'm not going to be precise, I'm going to be accurate. Because I probably am not going to be able to cut that 0.191 centimeter above 8 centimeters. These from the factory are about 7 centimeters. I'm going to at least cut them up another full centimeter to 8 when I cut them. 8.191 on each side would be best. I don't think I'll be able to cut the 191 accuracy, but I can cut the 8. And this is just a 9.009 from 0.2, a fifth of a centimeter. So I might be able to cut 8.4, 8.5 centimeters. And actually, I have a caliper. I can set it for 8.191 centimeters and cut it with that pretty precisely. Boy, that was a long way around the horn, wasn't it? But that's what I ran into when I got new antennas recently. And if you look down on the table again real quick,
these are the 2 little pieces of wire that I cut off the new antenna I got to cut the new antenna down to 915 megahertz. I had to cut this much off of each end, and I will cut this one. Like I say, I'm going to get out my calipers and set them for 8.191 centimeters and put one edge of the caliper on that solder joint right there and measure out here. Now it might technically be, although there's a little bit of gap between where the 2 antennas are soldered on there, electrically and electronically it may be as if they're touching, and I really should only have like 8 centimeters out here, and the electrical, the theoretical, the gap in the center there might actually fall into this calculation too. Not too sure about that one, but we're going to be accurate but not precise. So there's you a big heads up. All of your antennas, you should sort of check them and see if they're physically the way they should be when you get them. It's just my recommendation, and also this is how I do it. The 433 is almost twice the length of the 915, so you almost have another 915 antenna in these 2 short pieces that I cut off. All right, just some food for thought and a heads up. Thank you guys.
I thought I would stick this on the end while I was editing the video for uploading. If you take this antenna out of the box and put it on your 915 transmitter and your transmission goes all to pieces, I'm sure if you email Dragon Link support, they're going to tell you quickly, oh, those antennas have to be cut. I bet they're going to tell you to cut them 8 centimeters on each side. I, I just am a little shocked again that nothing comes in the box that says these are perfect for 433 but have to be cut for other frequencies. I'm shocked that I can't find anywhere on the internet that says it. I'm going to go back through those videos, but I don't think it was really down inside those videos that you have to cut these antennas. But I bet you dollars to donuts that Dragon Lake Support's going to say, yeah, for a 915 transmitter, you're going to need to cut this antenna. And I think after you got it and put it on incorrectly, just because you didn't notice that they're going to, and you have poor transmission and you say something to them, them new antennas I got just aren't worth a hoot. They're going to say, well, for your 915 system, you need to cut them 8 centimeters on each side. I just have no doubt of that whatsoever. I don't know that it's going to happen, but it just seems like they're good people. I just think they'd set you straight real quick, whereas it took me, almost an hour. Okay, I won't do many of these types of videos, but I thought this one needed to be out there on the internet someplace. Thank you.